Welcome to this hands-on AI for DevOps engineers projects. If you have been hearing about AI everywhere but wondering how it actually applies for DevOps, SRE, platform engineering or cloud, you are in the right place. In this video, we are going to build 4 production inspired AI projects that solve real DevOps problems. Not just ChatGPT prompts, not simple demos, real engineering projects that solve real production problems. First, we are going to start with an AI log investigator that intelligently analyzes production logs without blindly sending everything to an LLM. Then we are going to build an AI incident triage system that helps prioritize alerts so you know where to focus during a production incident. Then we'll build an AI Runbook Assistant that searches your documentation and runbooks to quickly find the right troubleshooting steps when production is under pressure. And finally, we'll build an AI Terraform Reviewer that automatically analyzes your infrastructure code and identifies security issues before deployment. The best part, every project in this video comes with the complete source code. I'll show you exactly how everything works, explain the architecture, write the code step by step, and by the end of this video, you will have 4 AI powered DevOps tools running on your own machine. Let's start by taking a quick look at the GitHub repository. Everything is here: the source code, documentation, sample data, project structure. You can just clone the repository, follow along, and build every project with me. Now, let's start with our first project, the AI Log Investigator. Many engineers are using AI completely wrong. And because of that, many companies are restricting AI usage. Not because AI is bad, not because AI doesn't work, but because engineers are doing like this. Production goes down, and engineer downloads huge log file that is around 50,000 or maybe 100,000 and then uploads everything into ChatGPT, Claude, or any other AI model which has a lot of information. For example, customer information, IP address, then sometimes internal host names. Then everyone is surprised when security teams start asking questions. Today, I'm going to show you a different approach. By the end of this video, you will learn how to safely use AI on production logs, how to remove sensitive information automatically, how to dramatically reduce token usage, how to use a local AI model, how to investigate incidents faster, how to keep humans in control. And the best part is that you can take this project and implement it in your own environment. Of course, every company is different. You may need to adjust log formats, some policies, and and AI models according to your requirements. This is not a toy prompt project. This is a practical DevOps project. Before we start, I have a small request. If you enjoy practical DevOps and AI projects like this, hit the like button. And if you want me to make this entire project public, including the code, architecture, setup instructions, and future episodes. Leave a comment below. If this video gets at least 100 comments, I'll make the complete project available for everyone. Now let's build it from scratch. Everything is already prepared. If you can see, I'll try to write a tree command. We have multiple different files ready. I'm going to explain each and everything in detail. First, let's try to understand architecture before we start. I'm going to jump back to my board once again, and here let me write it down. So first, we are going to check logs. This is how our workflow looks like. Followed by, we are going to sanitize those logs. Then we have a pattern extractor, and then we are going to talk about the token optimization as well, and finally AI analysis, and one last step is human validation. So this is our flow today. We are going to check logs, sanitize those logs. We are going to extract patterns. Also, we are going to talk about the token optimization within this workflow. AI is almost at the end. Most tutorials start with AI. We start with engineering. That's the difference. And finally, we have human validation. All right, let's jump into the Visual Studio Code once again. So here, as I said, our project is ready. I'm going to start with generating log files. So I'm going to run Python 3 generate logs.py, press enter. If you can see, it generated logs raw application.log with 50,000 log lines. In a real company, this could be Kubernetes logs or maybe Jenkins logs, Nginx logs, application logs. For this particular video, I am generating realistic production style logs. But these logs actually contain the same information which we actually see during real incidents. So first I'm going to run a simple command. For example, wc-l logs followed by raw application.log. Press enter. We have seen already 50,000 log lines here, and also I wanted to show you by running this command 50,000 lines. Now we have 50,000 lines of logs as you have seen in the terminal. Now imagine it's 1:30 a.m. midnight, production is down, customers are reporting errors, management want updates from us. Would you manually go read these 50,000 lines? Probably not. And that's why AI becomes attractive for us. But before we involve AI, let's understand what we are actually dealing with. I'm going to jump back to my Visual Studio Code once again. So first, we are going to run a simple command once again. Here I'm going to clear my screen. Head hyphen phi followed by logs raw application.log. Now look at this very carefully. If you look at here, I can see customer email details very clearly, customer.payment@example.org, followed by, and I can also see the IP address, and we have a API token as well. We have some request ID as well. This is exactly why security teams are nervous about AI. Many engineers like us see logs, AI sees data, but security teams sees risk. Now let's try to run tail-5 logs raw application.log. Now look at this particular information. Most engineers look at this and think, let me just copy this and paste it to any AI tool. But there are two problems here. So, number one problem is security. And the second problem is cost. And this is where things get interesting. Let's talk about something almost nobody discusses it online when they create AI tutorials. That is tokens. Nothing but AI currency. Most AI demos online look amazing. Someone uploads a huge log file. AI will give you an answer, not an issue. Everyone says, wow, this is amazing. I uploaded the log file, I got my answer, that's it. No one thinks about how much data did we send? How much did it cost? Would our company actually allow this? Let's think about our example. So 50,000 lines of log file we generated. Imagine this in a real production environment. I already showed you these logs contain customer emails, service names, request information, session information. I mean, we have a lot of stuff here. Now, we have several problems here once again. Number one here is cost, which I already discussed. AI models don't read files, right? They read tokens. The bigger the input, the more tokens you are going to consume. The more tokens you consume, the slower the response rate, and also the higher the cost. Now imagine a company processing incidents every day. Hundreds of engineers doing that. Thousands of investigations go on. Those costs add up very quickly. Now, we'll talk about one more problem. So, problem 2, which is noise. Most production incidents generate duplicate errors. I mean, if you are working in a production environment, definitely you are going to relate with whatever I'm talking here. You will see so many duplicate errors. You are going to see same timeout message multiple times, same exception messages, and also same connection failures again and again. Now think about this. Does AI need does AI need all of these duplicate lines of logs? AI needs only patterns. Problem number 3. Now let's talk about the problem number 3. Think about GDPR. Think about internal security policies, customer contracts, regulatory requirements. I mean, these are, let's say, very few problems. I'm trying to write it down here. Many companies explicitly prohibit uploading production data into external AI systems. Not because they hate AI, because they have responsibilities to customers whom they serve. Now let's talk about problem 4. This is a very huge problem. Context windows. I mean, many tools, many companies are, let's say, trying to solve this particular problem, but this is a huge problem. Even if the model supports huge context windows, I mean, some of the models are already doing that. Should we waste them on duplicate logs? What do you think? Let me know in the comments. I would probably say not. Good engineering is sending better information, not sending like more information to AI blindly. The goal is, how do I send better information to AI? That's exactly what we are building today, and we are going to solve this problem. Now let's jump back to our Visual Studio Code once again. So if you look at this particular screen, now I'm going to run a script which is Python 3 sanitizer.py. I'm going to run this particular script, and also I will try to explain it. Don't worry about the script explanation. This is where real magic begins. We are not removing useful information. We are just trying to remove the sensitive information. Now let's try to run the command head-3 logs raw application.log. So this is our raw application.log file which we generated in the beginning, followed by I'm going to run the sanitized log now. So let me run this. So this is our sanitized application.log, and this is our raw application.log. Now let's look at the difference. So if you see, previously we had critical service auth API user details, let's say the email. In this particular sanitized log, I can see, I cannot see anything. I see user equal to email, IP is equal to IP, and token request ID. Everything is hidden. The IP is gone, the token is gone, and also the request ID is gone. Because AI doesn't care whether this particular email belongs to Arbaz or not. AI only needs to understand there was an email like this. That's a huge difference. Now, let's look at the actual code what we have in this particular file. It's very, very simple. If you can see, it's, let's say, only 35-36 lines of code. What exactly we are doing here? Number one, it will try to find the sensitive information, right? Followed by, it will try to replace it with the placeholders. Okay, the placeholders which we saw in the output, email, IP, all of the details. Step 3 is nothing but we are trying to write a sanitized version of the logs. That's it. This is very, very simple, effective, and the practical use case I'm trying to show in this video. Now we are solving the second problem, which is noise. Press enter. So if you see, top 5 patterns. Production incidents are repetitive. The same error appears thousands of times. AI does not need to read every line, every copy, right? Now, this is already written to this particular file. I'm going to open that real quick. Cat reports incident summary.md. Now look at this. Imagine seeing database timeout, let's say multiple times, or you want to see this particular error message. The count was, let's say, 1678. It is better if we see something like this. Count, let's say, 1678 for this particular service auth API, and I can see the details. This particular line was written multiple times, 1600 times. Followed by, we can see for another service, 1677 times, then 1643. The list goes on. Which one is more useful? Let me know in the comments. What do you think? is this particular summary file is better or pasting the whole raw log file to the AI model? For me, this looks way better than pasting the raw file because this simple optimization alone can save enormous amounts of tokens. I'm going to show that as well. Just wait a minute. Now let's look at the pattern extractor.py file, what exactly it is trying to do. Again, this is a very simple file. We are trying to group patterns here. For example, I'm trying to give the details, input file, report directory, and the report file, and important levels here, error, critical, and warning. We are trying to remove the duplicate lines here and also trying to extract some patterns, followed by we are trying to write this particular report into this incident summary.md file. Think of this particular file like log compression for AI. Instead of sending noise, we are just sending the signal. Now let's jump to my favorite section, Python 3. I'm going to run this script, token estimator.py. I'm going to run this now. Press enter. Now let's look at the output. This is very interesting because this is where we measure the impact. Most AI tutorials which you see online will not discuss about this. Real engineers care about cost. Now let's compare this. Estimated tokens. This is raw application.log file. It has 50,000 lines. Estimated tokens 2439454. Then let's look at the sanitized application.log. It also has a lot of tokens. Then finally we have incident summary.md. It has 106 lines, estimated tokens 841. Now look at the difference. We try to reduce the amount of information that needs to be sent. This means we are going to send only 841 tokens. Here we have so many tokens and we compressed it almost to 841 tokens. I am going to copy this real quick and jump back here to my blackboard. Now, if you see, we are trying to reduce the summary to 99.97%. What does it mean exactly? That means we are going to get faster responses, followed by lower costs, better accuracy, smaller context requirements. How many of you agree with this? Let me know in the comments, what do you think? Will this save your time, also the money to the organization? Let me know in the comments, what do you think? Now let's jump back to our next part, Olama list. So I do have so many models right now. For this demo, I'm going to use Mistral model. So I'm going to run this script real quick, AI investigator.py. Press enter. If you see, this particular script is trying to send sanitized plus aggregated summary to local AI model. Now, if you remember the full flow, this is the first time AI enters the workflow. Notice how late that happens. AI is not step 1 in our full workflow. AI is at step 5. Now let's look at the response. We try to write the investigation report to this particular file. I'm going to open that real quick. Cat reports followed by AI investigation.md. Now let's go through what exactly AI is trying to tell here. Most likely the root cause appears to be a high load on Postgres database, leading to connection timeouts and exhaustion of the connection pool for multiple services. It mentioned the multiple services here. This could be due to an increase in traffic or poor database performance. Evidence from logs. The logs show repeated messages indicating critical issues such as Postgres max connections reached. Database connection timed out. Impacted systems. The primary impacted systems are Auth API, Checkout Service, Nginx Gateway, User Service. Recommended next steps. Check PostgreSQL logs for any errors or performance issues. Analyze database queries to identify slow running queries that might be causing the high load. Check if there is an increase in traffic that could be causing the load of the database. Investigate why background workers are failing. Monitor the response times of your service and identify any service that is consistently slow or returning 500 internal errors. Also, we have a confidence scores here, 80%. This score is subjective and based on the provided data, but the patterns of logs strongly suggest a database related issue. What human engineers must verify now? The human engineer must verify the current state of Postgres, including checking for high loads or slow queries, and investigate if there are any unusual traffic patterns that could be causing the increased load on the database. All right, now it is very clear according to the output. Now we are going to do a manual check once again. This is the step most AI demos are going to skip, which is verification. Because I want evidence, because production systems deserve evidence, not assumptions. I can clearly see the evidence here. This looks fine. I'm going to run one more command now. Grep connection pool exhausted log sanitized application.log. Now it clearly shows the error messages. It is not giving us assumptions. We have a proper direction. If AI tells me something, I want evidence, because production systems deserve evidence, not assumptions. AI gave us a direction. The engineer validates the results. That's how responsible AI adoption works. Now let's understand the AI investigator.py file, what exactly this particular file is doing. I'm going to briefly explain about this particular file as well. A lot of AI projects which you see online are over engineered, but the core idea is actually straightforward. The first thing we are doing here is loading the summarized incident report, not the raw logs or the sanitized logs which we generated, only the summarized patterns. This is a very important design decision, because we already spent lot of time to reduce the noise. Now AI will receive only the most important information. The next step is prompt construction, and this is where many AI projects fail. People think, let's send some data to AI and see what happens. That is not engineering, that is gambling. Instead, we tell the model exactly what role it should play. In our case, we are saying senior site reliability engineer, followed by we are providing some important rules here. Do not assume facts, do not invent services, give a confidence score, provide next investigation steps, keep the response practical for a DevOps engineer. Also, we are asking the written format, most likely root cause, evidence from logs, impacted systems, recommended next commands, confidence score, what human engineers must verify. Notice something in this particular prompt. We are forcing the structure. Structured outputs are much easier to consume than blindly AI generated paragraphs. Especially during an incident, midnight, we want what exactly happened and what is affected. That's exactly what we are asking the model to provide. Third step is we are using Olama here, local Mistral model. If you see Olama run Mistral in our Python file, because I wanted to run it locally. Majority of the organizations don't want to send their data outside their company. I mean, there are different ways to host ChatGPT models or Cloud Code models locally. But in this case, I don't want to talk about that. If you are interested, you can try with other models. I would like to keep it simple. I'm running it locally on my computer. I have a GPU based computer. Also, we can save a lot of money if we are using local model, and also I don't need to worry about tokens if we are doing local models. The final step is taking the AI response and saving it into a report. This is another practical design choice. Most engineers only try to print output to the terminal, but in real environments we usually want artifacts, so that it is very easy for me to read, and also I can attach it to the incidents, for example, if I'm working on that, and it would be useful in future. I am not sure how many of you noticed from the beginning, the AI part is actually one of the smallest parts of the entire workflow. Most of the work happened before AI was involved. For example, we did sanitization, we did pattern extraction, we also did token reduction, we did some data preparation. That's where engineering creates value. AI is simply helping us interpret the information faster. That's why I keep saying most tutorials start with AI, we start with engineering. Today, we build something I believe is far more realistic than most AI demos online. We did not blindly upload log files. Also, we did not trust AI blindly. We built guardrails. We reduced token usage a lot. We protected sensitive information being sent to AI models. We kept humans in the loop across the workflow. If you are a DevOps engineer or platform engineer, SRE, or cloud engineer, this is exactly the type of workflow I think we'll see inside real companies over the next few years. If you want the full project, remember the challenge: 100 comments below this particular video. If we reach 100 comments, I'll make the complete project public. And if enough people are interested, I'm going to continue this series and build AI Incident Triage Assistant, AI Terraform Reviewer, AI Runbook Assistant. Now, I want to hear from you in the comment section. Would your company allow AI to analyze production logs if those logs were sanitized first? Let me know in the comments. Thank you for watching and see you in the next video. Most production incidents don't start with clean alerts. They start with a lot of noise. CPU alert, memory alert, database alert, API latency alert, disk warning, the list goes on. Everything starts screaming at same time. And at midnight, the real question is not do we have alerts? The real question is which particular alert should we fix first? Because during a real production incident, time is limited. And if you are chasing the wrong alert, which many of us do, you can easily waste 30 to 45 minutes of time while customers are still affected. So, in today's video, we are going to build an AI incident triage assistant. By the end of this video, you will learn how to generate realistic production alerts, how incident triage actually works in large environments, how to score alerts using engineering rules before involving AI, how to identify customer impacting incidents automatically, how to build a risk scoring engine using Python, how to use Olama and Mistral locally, how to create structured AI incident reports, how to separate root cause candidates from symptoms, how to keep humans in control of production decisions, how to build a complete AI powered DevOps project that you can adapt in your own environments. And the best part is that this isn't just another AI prompt. This is the practical workflow. You can replace the fake alerts with Prometheus alerts, Grafana alerts, Datadog. I mean, it can be any kind of tool or technology that you are using in your own projects. The architecture will remain the same, but just like the previous project, we are not going to blindly trust AI. We are going to do this properly. Of course, every company has different services, different alert names, severity levels, and escalation rules. So you will need to adjust this for your particular environment, but the architecture absolutely works. If you enjoy practical AI and DevOps projects like this, hit the like button, subscribe if you are not already subscribed, and comment triage if you want me to make this full project public. Also, I need at least 100 comments on this project. Now, let's build it from scratch. First, let's talk about the real problem. In many companies, the problem is not that monitoring is missing. The problem is monitoring creates too much noise. I mean, if you are working in an organization or a project, definitely you can relate to whatever I'm trying to tell here. If not, that is also fine. You may have Prometheus or Grafana or Azure Monitor or maybe Datadog. Lot of alert rules, emails, channels. I mean, there is a lot. Everything here is, let's say, connected. But when something breaks, you don't get one perfect alert saying, here is the root cause. Instead, you get many related alerts. Maybe the database slows, or maybe API starts returning, some errors, something like 500 errors, or maybe checkout service latency increases, CPU goes high. So, as an engineer, you will see 50 different alerts and doesn't know what exactly to do first. This is exactly where an AI assistant can help you. Not replacing the engineer, but just organizing the chaos. The goal is not automatic remediation, but better triage. Now let's look at the project structure. The project structure is already ready. I did prepare everything. We have alerts folder, we have reports wherein all the reports will go. We have AI triage file, and we have generate alerts file, incident report file, risk scoring.py file. I can run this command real quick and show you the structure so that it's very clear. Now let's draw the architecture real quick. I'm going to go back to my blackboard once again. So the architecture is very, very simple. Alerts are, let's say, the first step, followed by we are going to do some risk scoring, and then we will have alert summary, AI triage, and then final incident report. Human validation is the last step. As I said, the architecture is very, very simple. We'll have alerts, we have some risk scoring system, alert summary, AI triage, final incident report, human validation. Notice again, AI is not the first step. We don't just throw 100 alerts and ask for the output, but we apply some engineering logic first. So that will happen here. Now let's jump back to our Visual Studio Code. First things first, to make this work, we need some alerts, right? First, we are going to generate the production alerts. For that, I'm going to say Python 3 generate alerts.py. Press enter. In a real company, these alerts come from Prometheus, Grafana, CloudWatch, Azure Monitor, or any other internal monitoring system. For this demo, I am trying to generate it from a Python script. The important thing here is not the alert source. Okay, it can be anything. The important thing I would like to talk here is, let's say, the full workflow that we are doing today. Now we have the data ready. Let's try to read that real quick. For that, I'm going to say cat space alerts followed by alerts.json, and I would like to read, let's say, first few lines. So I would say head 40. Press enter. Now, if you look at the structure, each alert has an alert ID with the number, followed by we have some timestamp, a service, a team, criticality, environment, region, severity. This is exactly what you are going to see in real production environments. And also, we can see the signal type here, latency, for example. This is very close to the type of metadata you would want in a real alerting workflow. Because if you only know only the CPU usage, for example, that is not enough. CPU high on a dev service is not the same as database unavailable in production. Now let's try to open the code real quick. So this is my generate alert.py script. So if you look at this very, very carefully, we define a list of services here. Postgres, auth, checkout. I mean, according to the environment, you can define that here. And also you can write it down, the criticality, the team, all the details can be, let's say, provided here. Then we define alert templates here. For example, we are trying to include database unavailable, connection pool exhausted, 500 spike, then checkout latency. The list goes on here, payment failure, pod restart loop, and all of that stuff. The script randomly generates 120 alerts, but I also intentionally make a few alerts more serious. For example, if you can see, Postgres is unavailable from application nodes and also the customer impact. This particular part gives us a realistic incident storyline because in a real outage, not every alert has the same importance. As I said, we see a lot of noise. Now let's go back to our second part. Let me clear the screen and I'm going to run risk scoring.py. Now, this is, let's say, the scoring engine. This is one of the most important parts of this particular project. Many people would try to send raw alerts directly to AI. I am not doing that here. Before AI gets involved, we should apply deterministic engineering logic here. So, if you look at here very, very carefully, we have top 5 alerts with a priority P1. For example, score is, let's say, 445. This is not AI. This is just pure engineering, and that's very, very, very important. Now let's look at the risk scoring.py. Let's walk through this particular file at a very, very, very high level. We start with score maps. For example, if you can see, we have a severity score, criticality score, signal score. High severity gets fewer points, medium and low gets lower scores. Then we score service criticality. A critical service like PostgreSDB or payment service gets more weight than a low impact service. Then we are going to score signal type. Availability and errors are more important than maintenance warnings. We are trying to calculate the risk score here. We are using the severity score, criticality score, signal score. Then we are giving the environment details here. For example, production means I'm going to give more 75 points here. Followed by, we are trying to add extra score for customer impact, and also the status firing is, let's say, few more points. This is simple but very, very powerful because this is how real triage happens. You don't look at alerts equally. You first ask, is it, let's say, production, or maybe is it, let's say, customer impact, or is it, let's say, still firing? Is the service critical? I mean, you'll ask multiple questions. Is this a symptom or a root cause? This particular script then sorts the alerts by risk score and writes a summary report as you've seen in the terminal. Now let's look at that particular report that got generated. For that, I'm going to say reports alert summary.md. Press enter. Now let's look at this very, very, very carefully. If you see alert triage summary, this summary was generated before AI analysis. We have total alerts 120, P1 59, P2 13, P3 34, P4 14. And also we can see the details here. Severity counts. Critical, we have 49, high 24, medium and low. Most noisy services. And the top 20 risk scored alerts. This is already useful without AI, and that is the point. If your system is useless without AI, AI will not magically fix it. AI should improve a good workflow, it should not hide a bad workflow. This particular summary reduces a lot of noise. If you look very, very carefully, instead of sending 120 raw alerts, we send the most important summary. Again, we are trying to follow the same pattern as project 1. Better data first, AI will come second. Now let's talk about the local model, Olama list. For this project, once again, I am going to use the same Mistral model which I did with my previous project. You could replace with another model. You could use GPT, Claude, Gemini. It's up to you. The model is not the main point here. The whole workflow is what matters a lot here. I'm using a local model because many companies are careful about sending operational data, especially outside their environment. Even though this is, let's say, kind of, a fake alerts which I try to generate, I don't want to use, any other models. I'm going with the local models. Now, let's try to run the triage script. Python 3 AI triage.py. This is where the real magic happens. Now we are trying to involve the AI. We are trying to send summarized alerts to a local AI model. As I said, we are not sending raw random alerts. We are sending a structured alert summary. The AI will only receive what we send, for example, top alerts, risk score, whatever we saw in that summary file. Now the AI has a lot of context to help us reason, but not so much noise that it gets confused. Now let's look at the AI AI triage.py file. Once again, this is very simple. The first thing it does is just read the alert summary report. Then it builds a prompt. The prompt tells the model you are a senior incident commander and site reliability engineer. You are reviewing a summarized and risk scored alert report. Important rules we are trying to give here, and also return the answer in the exact structure, because we don't want a generic chatbot answer. We want incident thinking. For example, if you see recommended incident priority P1, P2, P3, top incidents to investigate, likely root cause, escalation recommendations. I mean, we gave a lot of details in this particular prompt. This particular thing matters a lot because during an incident, nobody wants a random paragraph. We need a proper structured output like this. We need to know why it matters. Do we have any kind of evidence for this? Customer impact, how big is this? Recommended owner or team, should we escalate or not? This particular script sends the prompt to Olama, and also if you look here, we are trying to save this report. Again, we save the output as an artifact, not just terminal text that you saw just now, because in real incidents, reports matter a lot. You want to paste this particular report into Slack channel, or maybe attach it to an incident ticket, or use it as a post-mortem. This can be used, let's say, in multiple different ways. So it is better always to store this particular file. It can be useful in future incidents as well if you come across the same thing. Now let's look at the report very clearly. What do we have in the report? I will say cat slash reports AI triage report.md. Now look at this executive summary. There are a significant number of critical and high priority incidents affecting multiple services, with the majority of alerts being related to PostgreSQL database, HTTP 500 errors. Most noisy services are PostgreSDB, Redis cache, worker queue, all service, payment service, marketing site. I mean, I can see multiple different services. Recommended incident priority P1. Top incidents to investigate first. P1 score 445, database unavailable, alert ID I can see. Why it matters? PostgreSQL is the primary database for multiple services, and its unavailability can cause widespread service disruptions. Evidence: Postgres is unavailable from application nodes. Customer impact is true. Recommended owner or team database. So if you look at the output, we have the proper priority here. We can see the likely root cause candidate. We can see the symptoms as well. And also, I see immediate next commands or checks. Investigate Postgres unavailability and exhaustion of connection pool. In affected this particular regions, analyze HTTP 500 error logs, and also escalation recommendation we have. If the root cause cannot be identified within a reasonable time frame, escalate incident to on-call manager and engage the appropriate teams for further analysis and resolution. Finally, we have human validation checklist as well. Confirm Postgres unavailability, exhaustion, validate any adjustment made to server resources, confidence score 80% based on high volume of related alerts and the impact on multiple services. This is where AI becomes useful. It is not just listing alerts, it is explaining priority. That's the value. Alerting systems tell you something is wrong. Triage tells you what matters most. That difference is, let's say, very, very huge. Now we generate the final incident report. This combines the AI triage output with the pre-AI alert summary. Press enter. Now we have this written into an MD file, and it adds a human approval section. This is very, very important here because AI should not be the final decision maker, especially in production environments. Now let's try to understand incident underscore report.py file. Again, this is very, very simple. We are not doing a lot of stuff here. For example, we are just trying to take the summary file, AI report file, and we are trying to generate the final report file, combining these two files. Then we are trying to give an important note here. This report is generated by human in the loop AI incident triage workflow. Scrolling down, I can see pre-alert summary followed by human approval section as well. Before taking actions, use this. Is the highest priority alerts still firing? Is customer impact confirmed? Are related services showing symptoms? I mean, we are trying to take all of these actions. Then finally, we are trying to give some incident commander notes: current status, customer impact, suspected root cause, mitigation started, owner, next update time. Now let's look at this particular file real quick. Cat reports final incident dot md. Press enter. This particular final report is something you actually imagine using in a real workflow. It gives the incident commander a starting point. It summarizes alert storm. For example, if you can see top incidents to investigate first. This final report is something you can actually imagine using in a real workflow. It gives the incident commander a starting point. It summarizes the alert storm. It gives AI reasoning. It also gives some validation steps. And it creates a clean artifact. In a real company, you could extend this by sending the report to Slack, or maybe creating a Jira ticket, or maybe opening a pager duty incident, adding links to Grafana dashboard, pulling logs from Loki, or pulling metrics from Prometheus. This is where the project becomes more powerful. The final last step is human validation. Now let's do that real quick. I am going to clear the screen, and I would like to run some simple commands once again just to verify. Now let's try to validate this. I'm going to check PostgreSDB into this alert summary.md file. Press enter. Here we can see PostgreSDB 15 alerts, service PostgreSDB, max risk score is 445. The AI may recommend PostgreSDB or maybe checkout service as the highest priority, but we should not accept it blindly. We go back to the pre-AI summary. Do we see any kind of production alerts, customer impacts, or critical services? Do the scores support the recommendation? This is the same principle that we are trying to apply from project 1. AI helps us reason faster, but we as human beings, we need to validate that. I can see 14 different alerts in the checkout service. Now, let's try to summarize what we built today. This entire project can be summarized in 4 different steps. First, we started with alert chaos. We applied engineering logic here. AI helped us reason about priorities. And finally, humans validated the results. This is probably the most important lessons from both AI projects. Most people start with AI first. We started with engineering. Better inputs, better context, and also better outcomes. Then AI will become very, very useful. Lesson number 2. Not all alerts are equal. A database outage in production with customer impact should never be treated the same as a CPU warning in a development environment. Lesson number 3. Monitoring tools are very good at telling us that something happened. They are not always good at telling us what to do first. That's where triage becomes valuable. Lesson number 4. AI is really good at summarizing information. AI is also good at finding relationships, also good at organizing chaos, but AI should not be deciding what changes happen in production. Humans own that responsibility. This was project 2 in this AI for DevOps series. Next, we can go into several directions. AI Terraform Reviewer, as I said, AI Runbook Assistant. Let me know in the comments which one you want next. If you found value in this project, hit like and subscribe. And if you want the complete source code, comment triage, and also remember the challenge 100 comments on this particular video. If we get enough comments on this video, I'll make the full project public. Thank you for watching and see you in the next video. Production is down. Pager duty is ringing. Slack channel is exploding. Manager is asking for updates. Customers are affected. And now someone says, check the run book. But where is the run book? Confluence, GitHub, Slack, SharePoint, or maybe some old incident documents, or in someone's head. This is one of the most common problems that we see in each and every team. Most teams don't have documentation problems. They have a documentation retrieval problem. The information exists, it is somewhere sitting, but during an incident, finding the right information fast is the real challenge. So, in today's video, we are going to build an AI runbook assistant. By the end of this video, you will learn how to structure operational runbooks, how to build a searchable runbook index, how to retrieve the most relevant runbooks for an incident, how to use local AI with Olama and Mistral, how to generate incident specific guidance, how to create a final incidents guidance report, how to keep humans in control of production decisions, how to adapt this particular workflow for your own internal documentation. This is not just another chatbot demo. This is a practical DevOps workflow. You can replace the sample runbooks, which I am showing, with your own Confluence or GitHub README files or any other sources which you have. The architecture which I am going to show will remain the same. If you enjoy practical AI and DevOps projects, hit the like button, subscribe if you are not already subscribed to the channel, and comment Runbook if you want me to release the full source code that I am going to use in this video. Now let's build it from scratch. So, what exactly is the problem? Most companies already have documentation. They have run books, they have wiki pages. They have good old README files and some incident reports. There is a lot, but when production goes down, every team member will ask each other, where is the run book? This is common across multiple different companies, multiple projects. And also, not only where is the run book, which document is correct. And also, is the page outdated? Or let's say, who owns this particular service? And also, what should I check first? These are kind of very few points I'm trying to put it down here. This is why runbook retrieval matters. During an incident, first 10 minutes are extremely important. If an engineer is spending, let's say, those 10 minutes searching through documentation, those 10 minutes are very expensive. If the engineer with less experience follows the wrong runbook, that can make the incident worse. So, the goal of this project is very simple. Ask a question. Find the right runbook. Generate practical guidance. And also validate before taking any action. This is not about AI replacing engineers. This is about AI helping engineers find the right operational knowledge faster. Now let's look at the project structure. I'm going to jump back to the Visual Studio Code. Here we have a runbooks folder. This contains sample operational runbook. For example, I have these in place for this video. We also have an incidents folder. I have a sample incident in place. We have an index folder which is empty right now. This will store the searchable runbook index. We have a reports folder. This is where the retrieved runbooks, AI answer, and final guidance report will be generated. These are some Python files. For example, the main Python files are build underscore index. We have search underscore runbooks. And also we have AI runbook assistant.py. And finally, we have final report.py. The workflow is very simple. I'm going to write down the workflow here on the blackboard so that you understand the full architecture. We are going to start with incident question, followed by runbook index. Then we have relevant runbooks and AI guidance. Finally, human validation. Everything starts with an incident question. Production is slow, database latency is high, or payment failures are increasing. That's the real problem we are trying to solve today. Next, we organize knowledge. Our runbooks, our documentation, operational procedures are indexed and searchable. Then we try to retrieve most relevant runbooks according to the incident or problem which we are trying to search during an incident. This is important because AI should receive better context, not more context. Only now we are going to involve AI. AI reads the relevant runbooks and generate guidance for engineers. Then finally, we try to generate a final report which can be then validated by human. AI recommends, humans will decide. That's the exact pattern you are going to see in the whole series. Now let's jump back to our Visual Studio Code. Here, if you look at the runbooks, we have multiple different runbooks. For example, database latency, disk full, high CPU, Kubernetes crash loop backoff. These are, let's say, some common real world operational situations. In your company, these could be exported from Confluence or GitHub or any other location where you are storing these particular files. The format does not matter as much as the workflow. Let's try to open one of the sample incident. So this is the incident which we have. This is very simple. For example, checkout is slow and some users are seeing payment failures. Alerts, API latency is high, database connection pool exhausted, payment failure. Question, what should I check first? This is a simple incident. That's the kind of practical question this assistant should answer. Now, let's look at one of our runbooks. For example, database latency.md file. So, if you look at this particular MD file, it is a bit structured. I can see some symptoms here. API response time increases, checkout or login becomes slow, application logs show database timeout. It has first checks. For example, check database CPU and memory, check active database connections, check database connection pool setting, and some useful commands as well. kubectl logs deploy API service, kubectl top parts, kubectl get events, and some PostgreSQL examples as well. Finally, I can also see some common causes and also mitigation steps, escalation steps, and also final human validation. This is the kind of documents which we are going to see in our own projects. This is a bit structured, but in general, we will not have so structured or proper documentation. If our runbooks are, let's say, bad, AI output will also be messy. If we have better documentation, something like this, it might not be 100% correct, but 80 to 90%, this is okay. We will have better AI answer. That's the goal of this project that we are building today. Now let's start. So first, I'm going to build the index. For that, I'm going to say Python 3 followed by build index.py. Press enter. If you see index 6 runbooks. Index written to index runbook index.json file. Now let's look at the build index.py script. Again, this is very simple script. It's not very complicated stuff. First, this particular script will read all the markdown files which we have in our runbooks folder. So here we have multiple different runbooks files. It is trying to read that. Followed by it try to tokenize the content. Then it try to store the title, file, content, tokens, token count in a JSON index. This is a simple local search index. This is a simple local search index. In a production system, you might use embeddings, you might also use a vector database, you might use so many different, services, for example, Elasticsearch, OpenSearch, Chroma. I mean, we do have a lot of stuff. I don't want to dig deeper into all of that stuff, but for this demo, we are keeping it simple and understandable. The point is not to hide everything behind a framework. The point is, let's say, here to understand the full workflow which we are doing. Now let's look at the JSON file. So I have runbook index.json file created. So if you see, this is a very huge file with a lot of stuff. So for example, I can see file, title, content, tokens. As we wrote in our script, we have the exact format output here. Now let's try to run this real quick. This is how our structure looks like in JSON file. We have a file, title and content, and we have tokens as well. So this gives us a simple way to search for relevant documents. And again, this is not advanced RAG yet, but it shows you the core idea, converting documentation into searchable context and also retrieving the relevant pieces that are required during a production incident. Now let's search for relevant runbooks here. Our question mentions database latency is high and checkout is slow. What should I check first? In this case, the search system compares the question against the runbook index. Then we can see the output like this. Here it scores document based on keyword matches and important incident keywords. This brought back our runbooks, database latency, and payment failure. This is important because we don't want to send every runbook to AI. If a company has, for example, 500 runbooks, AI should not read all 500 every time. We try to retrieve the most relevant according to our incident and according to the problem. Now, let's look at the retrieved reports. Retrieved runbooks.md. This particular report shows which runbooks were retrieved. It also includes the user question which we asked, and also we can see top matches. For example, we can see the match score of 63 and a portion of the runbook content. This is just, let's say, the evidence layer. Before AI gives us an answer, we know what documents it is using. That matters because if AI gives a bad answer, we can check whether the wrong runbook was retrieved. In real systems, retrieval quality is more important than model quality. We can use a very big model. With bad context, we are going to get bad answers. A smaller model which we are doing in this particular video, for example, Mistral, with good context can be very useful. Now let's try to open search underscore runbooks.py file and let's see what do we have in there. I am going to explain this on a very high level. Again, this is a very simple script. We are not doing complex stuff here. First, we are trying to load the runbook index. Then we are trying to tokenize the user question. Followed by, here we are loading the index. Then we are giving a score. Each runbook based on matching terms. That means it will try to boost database, for example, boost latency, payment, crash loop backoff. I mean, this is, let's say, very common if you work in real production environment. Definitely you are going to relate. And certificate issues are, let's say, very common. Crash loop is, let's say, another common word. So this is how we are going to boost some keywords. Then it sorts the runbooks by score and returns the top matches. This is not perfect, but it is transparent. In a real system, you could replace with this embeddings, but even then, the concept stays the same. Now, let's jump back to our local models. So, I'm going to check for Olama. Here, I do have so many different models running locally on my computer. For this demo, I'm using Olama with Mistral. You can replace with GPT, Claude, Gemini. It's up to you, or any other model. The model is not the product here. The workflow is the product. I am using a local model in this video because I don't want to send company's data to the outside world, even if the data is not customer data. Because runbooks can reveal lot of details about our infrastructure, our internal architecture, service names. I mean, so many different things. So local AI can be very useful for internal DevOps tooling. Now let's try to ask our AI runbook assistant. Database latency is high and checkout is slow. Payment failures are increasing. What should I check first? Press enter. But notice what exactly is happening here. We are first retrieving relevant runbooks. Then we give those runbooks to AI as context. Then we ask it to answer using only that particular context. The retrieval part finds relevant documents and the generation part creates a useful answer. Without retrieval documents, AI may hallucinate. Now let's understand what exactly we have in AI Runbook Assistant. So I'm going to open this file. First, it takes the user question. Then it tries to call the search function to find relevant runbooks. And it will try to build context from retrieved runbooks. Then it will try to build a prompt. You are a senior site reliability engineer helping during a production incident. This is very important here because we don't want the model inventing random commands. We want it to use only our internal operational knowledge. Then we add some rules. Do not invent systems, commands, or facts that are not present in the runbooks. If information is missing, clearly say what needs human validation. Separate immediate checks. Keep humans in control of production decision. Be precise and practical. And also return the answer in this exact structure. Most relevant runbooks, likely cost to investigate, suggested mitigation options, human validation checklist, confidence score. This particular structure is very important during incidents because nobody wants a long essay at midnight 1:30 a.m. Engineers need clear guidance for the next steps. For example, what should I check? What commands should I run? Whom should I escalate? That's what this particular script generates. Now let's look at the AI runbook answer.md file. I can see most relevant runbooks according to our question which we asked and according to the incident. I can see payment and database in this. Here I can see immediate checks. It is asking me to check. It also gave me the exact commands that I can use during an incident. Just checking the log files, for example, here, getting the events details. And also I can see likely cost to investigate, for example, payment gateway outage, API or secret rotation, network connectivity issue, slow query introduced by recent deployment. It gave me, likely causes to investigate and also suggested mitigation options. We are not blindly following this, we are going to validate it. Then I also can see escalation recommendation. This is the exact stuff which we asked the model to give as an output in our prompt. That's what we can see in the output. And also I can see commands to run here, PostgreSQL examples here. Also we have human validation checklist. Payment alerts are high priority because they may be directly affecting revenue. Do not assume database is the root cause only because latency is high. Validate with metrics, logs, recent deployment, history, and query analysis. What not to do? Avoid making changes without first validating the issue and its cause. Do not ignore payment alerts. And I can see some confidence score as well. Now let's try to generate the final report. For that, I'm going to say Python 3 final report.py. Press enter. So I can see final incident guidance.md file got generated. So what do we have exactly in this final underscore report.py? This particular final report combines AI answer with the retrieved runbook evidence. It also adds a human approval section. If you can see, we are trying to verify and also take some inputs from human. Is this incident still active? Is customer impact confirmed? Do logs support this suspected issue? These are, let's say, some of the actions we are trying to ask from human. This is the difference between a chatbot answer and an operational workflow. Now let's look at our final incident guidance.md file. This final report is something you could imagine using during a real incident. You could paste it into Slack, attach it to the Jira ticket, attach it to the postmortem, send it to the incident commander, or use it as a starting point for troubleshooting. In a real company, you could extend this by reading GitHub runbooks, indexing service readmes, pulling service ownership. I mean, you can do a lot. Now this becomes a real internal DevOps AI assistant. Let's try to do another test now. I'm saying pod is in crash loop back off after deployment. What should I check? Press enter. We got the response here once again. Kubernetes crash loop back off runbook, and I can see the commands that I can run and also likely causes to investigate. For example, wrong Docker image, missing environment variable, config map missing. So whatever we have in our runbook, we are getting the same exact answer. Now let's look for disk usage is about 90% on production node. What should I do? We got an answer saying AI Runbook Assistant response. This full runbook, immediate checks. df-h, du, varlog, docker system df, kubectl describe node, likely cause to investigate. Log files growing rapidly. This is, let's say, one of the major concern that we see in real production environments. Old artifacts not removed is also another problem. Backup files stored locally. We can clearly see suggested mitigation options, escalation recommendations as well. So let's try to search for the last question. In this case, I will try to ask Now let's try to ask another interesting question. In this case, I am going to ask coffee machine is broken, what to do? Press enter. No relevant operational runbook was found for this particular question. This assistant is designed only for DevOps, SRE, platform engineering, and production incident runbooks. All right. All right. We tested different incidents, different questions. Now let's go back to our blackboard and summarize what we have did today. The four important lessons we learned today in this project is documentation is useless if nobody can find it. Retrieval quality matters more than model hype. AI should answer from runbooks, not imagination. Humans approve production actions. These are, let's say, the four important lessons that we learned from this project. Now, let's try to summarize what we built. We started with a common production problem. An engineer needs help during an incident. The documentation already exists. The challenge is finding the right information quickly. So, first, we try to organize the knowledge into structured runbooks. Then we built a retrieval layer to find the most relevant runbooks. Only after that, we involved AI. The AI doesn't answer from imagination, it answers from our runbooks, which we retrieved. Then it generated the guidance, and finally, a human validated everything before taking any action. That's the type of workflow we have to use because production systems are too important to blindly trust with AI. If you want this project, comment runbook below. If enough people are interested, I'll definitely release the full source code. In this series, the next episode is about AI Terraform Reviewer. Thank you for watching, and I'll see you in the next video. Terraform says configuration is valid. Pipeline is green. Pull request looks good. But there is a big problem. Terraform does not know your company's policies. Also, Terraform does not know production SSH should never be open to the internet. One more big problem is public storage access can expose customer data. These are very few things which I am trying to write down here, and this is exactly how small infra mistakes become real production incidents. So, in this video, we are going to build an AI Terraform Reviewer. Not a chatbot, not a magic AI tool, a simple practical workflow that scans Terraform code, finds policy violations, use AI to explain the risk, and generate a pull request style review report. By the end of this video, you will learn how to scan Terraform code before deployment, how to create simple policy checks, how to detect risky infrastructure patterns, how to calculate a compliance score, how to use local AI with Olama and Mistral, how to generate a Terraform review report, and finally, how to keep humans in control of production decisions. If you are new to my channel, like this video, subscribe, and comment Terraform Reviewer. Based on the comments, I am going to open source this full repository. Let's build it from scratch. Now let's try to understand the architecture. The workflow is very simple, as I said. First, we have Terraform code, followed by we have a policy scanner. Then we will have the findings. Once we have the findings, we are going to do a AI review. We are going to bring AI in the workflow. Then we have a final report. In the end, human validation. This is a mandatory step. So this is how our architecture looks like. We are going to scan some Terraform's code using a policy scanner. Once we get the output with findings, we are going to use AI to review that. And also we are going to generate a final report. Finally, human will look at the code and try to fix if there are any things to fix. Now let's look at the project structure. We have a Terraform folder with some bad code and some good code. Then we have some policies folder, we have reports folder, and we have three important files. One is AI Terraform Reviewer.py, final report.py, and Terraform policy scanner.py. So this is how our architecture looks like. And now let's look at the bad code first. So for example, here I can see a resource group being created using Terraform main.tf file. Followed by we have Azure network security group here. And if you look here, source address is 0.0.0/0. Destination is, let's say, star. Followed by we have security rules, allow RDP from internet. And then we have some logs which are being stored in a storage account. And here if you see, allow public access equal to true. Followed by we have MySQL Server, administrator, login, and password details are hard coded. And also we have some firewall rules. So this is how our bad code looks like. Now I'm going to show you some policies which we wrote for this particular project. We can add more and more policies according to the requirements. But for this video, I am keeping it a bit simple. If you look here, we have one of our policy rules.json file. Here I can see a policy name, severity, and the pattern, regex pattern we are using here, business risk, and recommendation. Then we have again no public RDP, name, critical, severity, pattern, business risk, recommendation. So we are trying to follow a pattern here. So these are all the policies which we have in place. Now let's try to run our Terraform policy scanner. This particular scanner will try to read the Terraform file in this particular folder, and it will try to generate findings like this. We can see some findings 6, and also we can see some compliance score, deployment decision, block deployment I can see, and also I can see that reports are being written to this particular folder policy underscore findings.md. Now let's look at the policy findings.md file. So if I scroll down here, if you see scanned file I can see, and also I can see the total findings, compliance score, and also deployment decision. Findings by severity, critical 4, high 1, medium 1. Below we can see the detailed findings. Critical, no public SSH. This is, let's say, coming from our policies which we define. For example, if you see line 26, business risk, Public SSH increases attack surface and may allow unauthorized access attempts. Recommendation: restrict SSH to a bastion host, VPN range, or private CIDR. Now, also it try to give us the details, exact match Terraform, for example, destination port range and also source address prefix. We have to go there to this particular file and change this. The same goes with no public RDP. Terraform badmain.tf line 38. It is mentioning the line as well. So let me go back real quick here. If you look here, line 38. So it is talking about this particular port in this finding. Restrict RDP to private admin networks or remove it. Followed by, we can see no hard-coded passwords or secrets. So hard-coded passwords may leak through source control, logs, or CI/CD output. Use key vault. Look here, it is telling us use key vault, environment variables, or a secure secret manager. So we have a clear findings of what all problems we have. Now let's quickly understand what exactly our policy scanner.py file is doing. So again, this is very simple file. If you are following this particular series, you already know what exactly we are trying to follow a pattern across all the projects which we are building. Here we have a policy file, policy rules.json. This is the file which we are defined in the beginning. Reports directory, findings, and findings MD. Followed by, we have some severity score, critical 100, high 70, medium, and low. Then we are trying to load the policies here. Followed by, we are trying to define the line numbers as well. Then we are trying to scan the file. So if you see, we are using scan file, and followed by, look here, we have policy ID, policy name, severity, file, all of this, business risk, recommendation, risk score. So if you have any specific thing that you want in your report, then you can add it here. That's so very simple. Now once we have that, we are going to define the compliance score and deployment decision as well, according to the severity. If it is, let's say, critical, block deployment severity is high, review required. And if it is low, we can ignore that. It completely depends. So for this video, I'm keeping it simple so that it is understandable. Now finally, we are trying to write all the reports into the reports folder. So this is what our Terraform policy underscore scanner.py file looks like. Now let's look at our models. So we are using the local models as usual. So for example, I'm going to run Olama space list, and if you see, over all the projects which we have done so far, I'm using Mistral latest once again. So I'm going to say Python 3 space AI Terraform Reviewer.py. So we are going to send the scanner findings to AI. So I'm going to explain in detail this particular file as well, but let's look at the output now. If you see, sending policy findings to local AI model. So blindly we are not sending all the Terraform code. We are trying to scan using our Terraform policy scanner, and then we are trying to send that particular report to the local AI model. This AI receives the policy findings and explain them like a senior DevSecOps engineer. This also reduces hallucination and also give us the better output. Now let's look at the review report. So AI Terraform review.md. So if you look here, it clearly gives us the executive summary. Terraform policy scan of Terraform bad main.tf has revealed several critical high and medium severity issues that pose significant risk to the security and compliance of your infrastructure. The most pressing concerns are the absence of firewall rules as for SSH, RDP, SQL, and storage blobs open to public access. And also, let's say here we got an overview. I don't need to read the full document, but overall we got an idea what exactly is this particular file talking about. Now, if you see deployment recommendation as well, given the critical blockers identified, it is strongly recommended that deployment be blocked until these issues are addressed adequately. And then also I can see the critical blockers. No public SSH, no public RDP, no hard coded passwords, no SQL firewall open to the world. Now, if you see high or medium issues, no public blob access. And also I can see recommended fix order. Address the critical blockers P01 policy 1, 2, 5 and 6. First by implementing firewall rules, removing hard coded passwords and restricting access to private networks for SSH. Next, focus on implementing the high severity recommendation policy 3 by setting allow public access to false in your Terraform configuration. Lastly, tackle medium severity issues. Then also I can see the pull request comment here. Human review checklist. Review Terraform configuration files to ensure that all findings have been addressed correctly. This is where human technical knowledge is very, very important. If you don't know the infrastructure, if you don't know the security, then AI cannot help you here, because AI can just give you this data and also it can fix, but you are the decision maker here. That's what human control, that's where let's say human control is very, very important. Test the updated infrastructure in a non-production environment before deploying it to production. This is also very, very important. Update CI/CD pipeline configuration if necessary to account for any changes made during this review. Verify that the newly deployed infrastructure is secure and compliant with relevant security standards and guidelines. Now let's look at the AI Terraform Reviewer.py. So what exactly we are doing here? We are using this policy findings.md file, and then we are building a prompt saying you are a senior DevSecOps engineer reviewing Terraform policy findings. Use only the findings below. Important rules. Do not invent resources or violations. Explain business risk clearly. Separate critical blockers from lower risk items. Recommend a fixed order. Keep humans in control of production decisions. This point is, let's say, very, very common across all the projects which we have built so far. Return the answer in this structure: AI Terraform review, executive summary, deployment recommendation, critical blockers, high or medium issues, recommended fix order, human review checklist. Then finally we are using Olama. I am using Olama local model here, Mistral for example. You can use any model of your choice. If you have access to ChatGPT, Claude, Sonnet, I mean any model is fine. I am using it local model because I don't want to send my data, and also I have a GPU based computer, so I am using a local model here. Finally, we are writing all this to a file which we already saw. Then once this is done, one final step is, let's say, run the final report. So Python 3 space final report.py. This will combine the AI explanation and the scanner evidence. Press enter. Now let's look at the final PR review.md file. Executive decision summary, deployment decision, blog deployment. I can see the compliance score 49 out of 100, total findings 6, severity breakdown as well. Critical 4, high 1, medium 1. Reviewer recommendation, and also we have top fix priority. It's almost similar to what we got from our scanner findings, but we are trying to combine the Terraform review.md and also our policy findings.md and making a final PR review.md. So it might look similar, but very important point here is clearly I can see the final PR status, recommendation status saying blog deployment. Whereas now let's try to run the second one, Terraform fixed main.tf, and I'm going to run the Python 3 final report.py once again. Now let's look at the final review.md file. Here I can clearly see recommendation status approve. Now if we look at the executive decision summary, deployment decision approve, compliance score 100 out of 100, total findings 0, security severity breakdown I do not see anything, reviewer recommendation, top fixed priority, no policy violations found, AI Terraform review 100 out of 100, deployment recommendation adheres to all established policies and best practices, no critical blockers. So this looks good. This is how we are trying to generate the final PR review.md, and also I can try to approve this pull request without any issues. At this point, you might be thinking, why do we need to build a particular tool if we have something like Chekhov, TFSec, Trivi, or let's say TerraScan? You might have a question that all of this already exists. That's a very good question, I would say. These tools are, let's say, very excellent. In production, many teams are already using all of these tools. We also did a series using these tools on our channel. This project is not trying to replace these tools. The purpose here is to understand how AI can fit into a Terraform governance workflow. Traditional scanners answer what is wrong, right? For example, Trivi or TFSec or TerraScan can answer what exactly is wrong. But this project, what we are building, also asks, why does it matter? What should be fixed first? How can this be explained in a pull request? So, if you remember the output, this is where AI is adding value to this project. These all scanners still provide evidence, but AI helps humans understands the evidence faster. Now, let me show something important. AI should not approve Terraform. Also, AI should not apply Terraform, override policies, because infrastructure affects customers, revenue, security, compliance, also availability. AI should always help engineers review Terraform faster. AI should not automatically approve production changes. AI will explain evidence. Humans should make the decision. And this is the workflow that we have built. Let's summarize what we built so far. We started with Terraform code. The code looked valid. Then we applied policy checks. Scanner found the real security issues. Then AI explained us those risks. Then we generated a pull request ready report. Finally, as a human, we are going to validate before deploying. This is a realistic workflow that can be trusted in production environments. If you enjoyed this particular project, let me know what AI plus DevOps project you want to see on the channel, and also comment Terraform Reviewer so that I know that you are interested in this particular project. Also, if we have more interest, I am going to make the full source code public. Thank you for watching and see you in the next video.